So we have our midterm 2 for CoCO tomorrow, Thursday, July 23rd. It is going to be during the regular class time. So the agenda for today is just talk about some logistical details of the exam, um, the reference sheets that you are allowed to use during the exam, some example problems, the format of the exam, and then I'll take your questions. So the exam time is going to start at the regular start of class time, which is 8 a.m. Eastern time, and it will end at 10:05 a.m. Eastern time. However, like I did in the previous exam, I recommend that you stop writing at 9:45 a.m. and then use the last 20 minutes for scanning and uploading things onto Gradescope. So 9:45. Oh, right here. I just I'll highlight this. So I recommend that you use the last 20 minutes, 9:45 to 10:05, for uploading your papers. And more or less you're following the same sort of methodology. My recommendation will be that you answer one question per page, just so that while you upload, it'll be easier for you to map the pages to the problem numbers. Let's see. You are required to show all your work. What is allowed during the exam? There are 2 reference sheets that I uploaded to the Piazza page for the class under resources, under midterm 2 resources. One is the Boolean algebra properties page from exam 1. This will be there as a resource even for exam 2. And also for flip-flop conversions, you will need the next tables and excitation tables of the 4 sequential elements: SR, JK, toggle, and data. So those will be there. I highly recommend that you go to the midterm 2 resources and check the reference sheets before the exam, so you know what you are going to have access to. You're also allowed a non-communicating calculator. However, I don't think you will need to use it. There are going to be no base conversions like you had in the exam 1. So you will have access to the non-communicating calculator, but I don't see any reason why you would need to use it during the exam. And of course, you will need your writing supplies to actually write the exam. As usual, you're using your own paper. Please do not write on the exam the question paper, because I have not left enough space. All of these things are very similar to exam 1, so you guys should be familiar with what's going to happen. All right, so those are some timing details. Next, where is the exam going to be? Please join the regular WebEx meeting at 7:45 a.m. So 15 minutes before the start of class, join the meeting, and I have provided the link over here, which you can access if you open up the PDF, which I'll be uploading to Piazza later during the day. This is the same link as the regular class link, so you can get to the WebEx meeting either way. So same as regular class meeting link. So you can get to it using either option. So you make sure that you join at 7:45 a.m. So that we get set up with proctoring. We also make sure that you have the resources of Boolean algebra properties and the next state tables, excitation tables, and so on. You make sure that you have the calculator and writing supplies. And then once everybody is set up, I will make the exam available to you using the file transfer option, just as I did in the previous exam. File transfer option. And for those of you who have access, a quick access to a printer, you will have the option to print it. So if I remember correctly, during exam 1, I made it available just, I think 5 minutes before the start of exam at 8 a.m. And I will do the same tomorrow. So in the 7:55 to 8 a.m. time, you will, if you can access your printer, if you have it, it's not a requirement, of course. If you have access to it, and if you like to use the printed exam, then you can print it out during that time. And as I said before, you are required to use paper to write the exam, your own paper. And as soon as you see the time to be 8 a.m., you can start answering questions. During the exam, you will be asked to keep your camera on and microphone on so that I can see you and hear you. Now, if you are uncomfortable with the background, you can use a fake background in WebEx. So even that is okay. But you will be required to keep your camera on and microphone on the entire time. However, you will be asked to turn off your computer volume so that you don't hear anything on the channel, any noise that might be happening that comes from the other student. So you will be asked to turn off your computer volume. And if you have any question during the exam, please type in private questions just to me, directly to me, and I will respond right away. So nothing new here. Like you guys have done this once before. So I hope none of this is coming as a surprise. Keep moving. What are the topics that are going to be tested on? The first topic is the topic of glitches and hazards. There's a lot of terminology that we had when we went over this topic. Static 1 hazard, static 0 hazard, accidental 0, accidental 1, SOP hazard, POS hazard, function hazard, dynamic hazard, static hazard, redundant prime implicant. So there was a lot of terminology that we needed in order to fix, right? That's what we did. The main thing that we did in this topic was we tried to fix static hazards. And you should expect a question on that, trying to figure out whether there is a possibility of a glitch or not, and then how do you fix that static hazard. So I would refer you back to, the back exams that I have posted on Piazza. Take a look at what you have over there for an example. So terminology, how do you fix static hazards? First of all, recognize which type of hazard you have. You may have SOP hazard, you may have POS hazard, depending on your synthesis, right? If you are synthesizing your function in the SOP form, then you may have a SOP hazard that is possible. So you have to first recognize which type it is and then try to fix it. And then, the Boolean algebra theorem that plays a crucial role in fixing static hazard is the consensus theorem. So all of that is the first topic that is going to be tested on. And I'm just highlighting fixing static hazard because I want you guys to expect a question there. Now, my recommendation with respect to glitches and hazard is, because this was a long time ago, if I were preparing for this exam, I would start with glitches and hazards because it was fairly, long time ago. So you might have forgotten a few terminology things. So a quick recap, or even watching the video on glitches and hazards can be very helpful. And today I also plan to do an example problem on this, so you can ask me questions at that time. Next main topic is the combinational logic design part 1. We focused on decoders, encoders, and tri-state devices in that. With respect to decoders, we just looked at how can I design some 2 to 4, 3 to 8 decoders. We looked at the 74X138 and 74X139 chips. Those were standard decoder chips. In one of the previous classes, there was a question about whether you need to remember the numbers. So I would like to point out again that you don't need to remember any of the IC numbers. If I have a question about a 3 to 8 decoder, then I will cite the number as well as its main function. And in most cases, I also give you the symbol of the decoder. So to get a sense of what you are expected to remember and what you are expected not to remember, please take a look at some back exams and you will get a fairly good idea about what is expected of you in terms of memorizing. That element should be very little, right, to memorize things. Then we went into the concept of basic and priority encoders. You guys also did a studio on decoders and encoders, and my goal with that was, once you do a studio, you actually see the decoders and encoders operate working, so that will solidify that understanding, which was mainly logic expressions, draw schematic and symbols, but when you actually see it to work, it kind of solidifies those ideas. Then we had the tri-state devices, a buffer in which you could have active low or active high inputs and outputs with an enable that will allow the outputs to be in the high impedance state. And we use that mainly because if you wanted to connect multiple outputs together, and if you're sharing a bus or maybe a 1-bit party line, then you can use this tri-state device so as to have only one signal control that 1-bit party line, which essentially becomes a problem while writing to the party line, not a problem while you're reading from the party line, because everybody can read from it. And there's a very nice problem in the spring 2019 back exam that I recommend you to take. I can actually look up that problem number. Let's see. This was problem 12. So problem 12 on spring 19 back exam. It's a a very interesting problem. It has a very funny answer as well. So I recommend you to go through that problem. It actually covers tri-state devices as well as decoders in that one problem. But it's an analysis problem. So it's about how you, given a circuit, how do you analyze its behavior. All right, so that's the second topic. Next, you have Combinational Logic Design 2, Part 2, where we went over multiplexers, demultiplexers, comparators, and adders. In adders, we went over ripple carry as well as carry look-ahead adder. Even though all these topics are pretty important, multiplexers happens to be one of my very favorite components, combinational components. Just because you can do a lot with multiplexers. Remember, you can also, do a lot with decoders, right? So you can synthesize logic functions using decoders as well. When I talk about multiplexers, using Shannon's expansion, you should expect a question there. How can I use a Shannon's expansion theorem to synthesize a logic function using a 2:1 mux, a 4:1 mux, an 8:1 mux, and so on. And also it can be reversed, right? So given a mux design, tell me the behavior of that mux design. So I would encourage you to look at some back exams for that from spring 2019. Both sorts of design and analysis problems are part of that exam. So take a look at that. And then we had demultiplexers, and then we had the big comparator 74x 682. Something that allows us to compare 8-bit numbers, and it gives you two outputs, equal to and greater than. And using those two outputs, you can derive all the other 6 inequalities, right? Equal to, not equal to, greater than or equal to, less than or equal to, less than. So you can do all the 6 comparison outputs just using those two, equal and greater than. Now with this, what I'm expecting is if the application of the analysis. So when we tried to design a 4-bit comparator, we started off with writing logic expressions. How did we write logic expressions? Using exclusive NOR gates for equal, and then how did we go from there to write a logic expression for greater than, and then using the two outputs, how did we write a logic expression for less than? So I'm going to try to test that aspect of comparators. Next, we had adders. Why did we go to carry look ahead adder? What was the bottleneck? Why is there so much focus on carries, right? So those ideas, we did a pretty detailed analysis using logic expressions to go from a ripple carry adder, which was slow, and it depended on the number of bits that we were trying to add, and we went to a carry look ahead adder, which had a problem of fan in, because the sum of the gates, if you're adding up more and more number of bits together, then the number of inputs to a gate will increase. However, the time it takes to complete the addition will be independent of the number of bits that you're trying to add. So 4-bit addition will take the same time as 8-bit addition, and so on, which is not the case in the case of ripple carry adder. And again, there is a problem in the back exam in which I ask you to calculate the gate delays for ripple carry and carry look ahead adder to do a comparison almost. So I would encourage you to take a look at that as well. Now, coming to latches, where we essentially moved away from combinational elements which did not have any memory to things that had memory, right, and had the ability to store information, bits of information. We started off with the set reset latch, which was based on NOR gates, the concept of metastability, the concept of bistable nature in SR latches. Why did we go from SR latch to SR latch with enable? The problem that we had over there was we did not want both the inputs S and R to be 1, 1, and even worse, we did not. We had metastability if we made those two inputs go from 1, 1 to 0, 0 at the same time. So that was our main problem, because that meant that the outputs would keep going between 0 and 1. And we fixed that problem by using an enable that allowed us to store information. And then we were able to tie the inputs together with a NOT gate in the middle. And that's how we went into the D latch. And that essentially meant that we are never going to have SNR 0, 0 or SNR 1, 1. And then we leveraged the enable signal to do our storing. And the last latch we looked at was the JK latch, which is essentially a combination of set reset and also a toggle functionality. So the symbol of latches, the characteristic equations. I should probably write them over here. So let's say the symbols, characteristic equations and tables. So, there might be a temptation to sort of memorize these characteristic equations in tables, but I want you guys to try to use the name of the latch, right, to to help you figure out what that equation is going to be or the table is going to be. So set reset, right? I want the output to set. I want the output to reset, and I want to have the ability to store, right? D latch, data latch. So whatever goes in will appear at the output after your enable is activated. JK, jump and kill. It'll also have toggle ability. So try to, blindly not try to remember the characteristic equations or tables, but be able to associate them with the name of the latch. And the whole idea over here is feedback, right? Feedback is what is allowing us to store that bit of information. Now, when we move to the last topic essentially for on the exam, which is flip-flops, one thing that is crucial is what is the reason we went to flip-flop, right? What is the main difference between a latch and a flip-flop? And I will do a problem in just a few minutes to illustrate that behavior. So that's kind of a very crucial piece. The type of flip-flops that we looked at, SR, JK, and a toggle flip-flop, their timing waveforms, their timing parameters of interest, the setup time and a hold time, apart from, of course, the propagation delay. Then this is probably highlighted now. Conversion of a flip-flop to any other flip-flop. No guesses there. This problem will appear on the exam. I will give you a known flip-flop or a unknown flip-flop, and I will ask you to convert it to some other flip-flop. So again, I'll direct you to back exams to take a look at some examples there. And I think during the class for this, we actually did a pretty interesting example where one of the students in the class essentially came up with his own characteristic table, the next state table for a flip-flop. And then we derived his flip-flop. We called it AN flip-flop using a JK flip-flop. So I think that example was pretty good, but take a look at some back exam examples as well. And then the last thing that I have over here is the next state tables and excitation tables of all the flip-flops. So you should be able to use these to help with the conversion problem. And for the known flip-flops, you will have access to those next state tables and excitation tables in the reference sheet. Okay. Next, coming to the format of the exam, it's going to be pretty similar to exam 1. There are going to be around 8 free response questions. They will be partial credit. Some questions may have parts, part A, part B, and so on. And none of this is new. This is very similar to exam 1. The main difference in sort of the format and the timing aspect of exam 2 is going to be that exam 2 should technically take less time to answer compared to exam 1. And primarily what is helping us save time is that there are no base conversions. Base conversions in exam 1 typically takes the longest time, and you almost have to slow down in order to get a correct answer. So that is not going to be part of exam 1, which will help with the maintaining that 8 to 9:45 a.m. Eastern timing. So my guess is some students are going to finish in probably an hour or less. And so for some students, it might go a little bit longer. Of course, it depends on student to student. It varies from student to student. But my expectation is that it should take significantly less time compared to exam 1. Okay, let's see. before I start off with some example problems, maybe I can take some questions here. So questions about topics, logistics, format. Please feel free to use your mic to ask the question. All right, no questions yet. Okay, I'm gonna assume that you guys don't have questions. I have a question about homework now. Roma, can we probably take your question at the end of this, because I have a couple of problems over here, and as soon as I get done with them, we can take your question. All right, so let's talk about this example, which is, I like this idea of comparison between a latch and a flip-flop all in one problem. So on the left, what you have is a circuit diagram, a schematic diagram in which there are some D flip-flops and D latches. Now, based on the symbols, I can recognize what each of these three things are. So for example, I see a triangle over here, which indicates that that is a positive edge triggered D flip-flop. Positive edge triggered D flip-flop. Then you have a triangle with a bubble in front, which indicates that this is a negative edge triggered D flip-flop. And the topmost block is does not have any triangle. It just has a CLK input or a C input, which essentially indicates that it is a latch, D latch. You are also given that these three elements have the same D input, which has been sketched over here. An arbitrary timing waveform for the data input has been provided. And also the clock signal. Let's see, maybe I can use something else here. Green. The clock signal given to you and is common to all of these elements. So D is given, clock is given, one of them is a latch, the other one is a positive edge triggered D flip-flop, and the third one is a negative edge triggered D flip-flop. Now let's suppose that our question is to sketch the timing waveform for QA, QB, and QC. So I want to find out or sketch the timing waveform for the three outputs. Let us start with the first one. For the first one, you know that Q changes, or I should say QA changes, when C equals 1, or I should say CLK equals 1. Latches are level sensitive. So as when the clock input is 1 or high, the output of that latch will be able to change. If CLK is 0, it does not change, meaning it is stored. If that is the case, let us see. When is clock 1? All right, let us highlight it, say yellow. Clock is 1 here and clock is 1 over there. And during that time, when clock is 1, QA is going to change. And how does it change? Well, it will simply follow the D input, because QA plus equals D. That is the characteristic equation for the D latch. So for the D latch, I'm going to say this: QA plus equals D. So let's try to sketch it out. What is QA going to be? Well, let's do QA over here. QA is going to be 1 and 0 over there, right? Because that is exactly matching up the D input. But the question is, what is it before that time? So what is it before it reaches that particular time? Well, you can make an assumption that it is 0, or to leave it as a general answer, you can say that I don't care. X, I don't know what it is. Might be a 0, might be a 1, I don't know. However, I do know that soon after the clock goes 1, QA will follow D. So let's see. I'm going to have that, and then I'm going to have that, and then I'm going to have that. So it matches D during that time. After that, clock is 0, which means it is latched, it is stored. So it will continue to be a 0. Now it is not going to respond to any of these changes that happen in D. It will continue until that time. Next, as soon as clock goes to 1, now QA will follow the D input. So now it needs to go high, low, high. All right, so let's do that. And then after that, it is stored. Right. So during these times, it is exactly high, low, high, low, high, low, high, low. It follows D during those times. So that's the latch behavior. Now we have assumed that the propagation delay of the D latch is very minimal, almost 0. But if there is some delay, then you might have to skew the output waveform to the right by a little bit to show that there is some propagation delay. Next, QB and QC. Let us try to do them. QB is positive edge triggered D flip-flop, which means that I only have to worry about, let me erase this guy, this guy, this guy, and then only focus on the positive edges of the clock signal. So let me sketch those out over here, positive edges, and that's it. I only have 2 positive edges of the clock. That's it, that I've highlighted. So the output QB can only change at those 2 instances. That's it. That's all it can do. Apart from that, it is stored. So let me draw that output waveform maybe in red. So at the first positive edge, what is the data input? 1. So at that moment, or soon after that moment, it will become 1 and it will stay that until the next one. Before that, however, I don't know what it is going to be. I can assume that it is 0, but if I have to leave it as a general answer, then I don't know what is going to happen before the first positive edge. But after the first positive edge, QB plus equals D. So at that moment, it was D, D was 1. So the flip-flop output became 1. And now it cannot change until it hits the next positive edge. So at the next positive edge, what is D? D is still 1. So it will continue to be a 1 there. It's never going to come back to 0. That's it. It's positive edge triggered, D was 1 there, D was 1 there, and there's nothing else that is left over here. Questions about how I have sketched QB? Let me write QB here. All right, let's try it. Let's take a look at the last one now. QC. For QC, I only need to worry about the negative edge of the clock. So I'm going to erase the positive edges, and I'm going to highlight the negative edges maybe in green here, go all the way down there, go all the way down there. Okay. So QC, let's do it in black. QC, the first negative edge happens at that time. At that time, D is 0, so it will be 0 from here to here. And at the next negative edge, D is 1, so it's going to move to 1 here. So 0, well, to avoid any confusion, I can just do this. But before the first negative edge of the clock, I don't know what QC is going to be. Again, I can make an assumption that all output starts at a 0, in which case I just draw that. But if I want to leave my answer in a very general format, I'm going to say that I don't know what it is going to be until the first negative edge. So I'll say it might have been a 0, or it might have been a 1. Another one there. I don't know during that time. So this is how you would essentially sketch the output of the latch D flip-flop, negative edge triggered D flip-flop. Okay. Any questions right now? All right. Let us move on and take a look at this. So this is a question about glitches and hazards. I'm going to assume that we are going for an SOP form of synthesis, which means that I'm combining the ones in the K-map. There are 4 inputs, A, B, C, and D. Let us say the output is F. So if I wanted to first do the simplest, SOP, what would I do? I would start combining the ones. So I may have this. That's a group of 4. This will be a group of 2. This will be a group of 4 here. And that will be a group of 4 there. Right. So depending on what they are, since I'm doing this in a SOP format, I can quickly write those terms, product terms. Let us try to see what that is. This will be C and D complement. This guy is going to be B is 0, and let's see, C is 1, and then this guy is going to be what? B is 1 here, C is 0 here, D is 1 here. Then I'm left with one more, which is that block there, which is A complement and C, right? So the simplest is going to be what? Simplest is going to be F equals A complement and C, or C and D complement, or B complement and C, or B and C complement and D. All right, so that's the simplest SOP form. Now, let us say we have to figure out in red if there are any hazards that are present in this synthesis. So suppose we have synthesized our function given in step number 1 in the simplest form. Then it is very clear that there is a problem at that place, right? We have not covered that. So I know that there is going to be a static 1 hazard present over here. Static 1 hazard because I'm going for a simplest SOP form. So I have a what hazard? SOP hazard present, which is also called as the static 1 hazard. It's also called as the accidental 0 hazard. But there is one that is present because there is clearly a RPI, redundant prime implicant, that I can add to this. And I see that there is only one here that I could do. So in step number 3, I will try to fix this. So I'm essentially going to, well, in step number 3, let's do this. In step number 3, let us write what that hazard is, right? So I want to explicitly write when that glitch occurs. And as you can see, the glitch occurs here. Come on. So how can I state the condition? Right. The condition is the accidental 0 happens when what is changing over here? C is changing. When C changes from 1 to 0, and it only happens from 1 to 0. For SOP hazards, that change has to be from 1 to 0. For POS hazards, the change has to be from 0 to 1 for a accidental 1 to happen. So accidental 0 happens when C changes from 1 to 0, while the other inputs, while A equals 0 and B equals 1 and D equals 1. So that's essentially how you would state the condition where the accidental 0 happens, right? So that's where the possibility is, because we have not covered that redundant prime implicant. There is only one here that is present. So let me write that. What is that term? That term is let's see, A complement and B and D, right? So how do you fix it? Well, you fix it by adding. So fix is by adding that particular hazard cover term, right, that I've shown in red. So I just appended that to my answer for step number 1. So we found out the simplest SOP, and then assuming that we have synthesized this function using the simplest SOP form, we answered 2 and 3. The part 2 was identify, like, terminology things, okay, if there is a hazard or not, static, which type it is. And then the third one was we explicitly wrote out all the possible hazard conditions. In this case, there was only one. And then we fixed that hazard, static 1 hazard. All right. So in terms of our discussion, I had only this much planned, so I'm going to stop the recording here, and then I will take your questions.